Hello everyone, let's analyze. So today we're going to talk about sequences and the limits they converge to. So consider this number or this one. Is either of these things a number? What would it mean that they're a number? The ... suggests that something infinite is happening. But what exactly? And what would it mean that in this infinite progress that's being suggested, that this is actually equal to a number? One way to think about it is, as you continue along this infinite ... path, does it get ever and ever closer to a number? In other words, does the square root of 1, the square root of 1 plus the square root of 1, the square root of 1 plus the square root of 1 plus the square root of 1, the square root of 1 plus the square root of 1 plus the square root of 1 plus the square root of 1, etc., and forever, creep closer and closer to a particular number the more I continue? Or does 1 plus the reciprocal of 1, 1 plus the reciprocal of 1 plus the reciprocal of 1, 1 plus the reciprocal of 1 plus the reciprocal of 1 plus the reciprocal, and so on forever and ever, does that creep closer and closer to a particular number the more I continue? So to investigate, let's index these listed numbers. In other words, let's write which number belongs in which entry in a sequence of numbers. So for example, for the first possible number, we'll say a1 is the square root of 1. a2 is the square root of 1 plus the square root of 1. a3 is the square root of 1 plus the square root of 1 plus the square root of 1. a4, similarly, the square root of 1 plus the square root of 1 plus the square root of 1 plus the square root of 1. So forth and forever. In fact, for each of these, we can see that each new term is the square root of 1 plus the previous term. Right? Here, for a4, we have the square root of 1 plus, well, that's just a3. And for a3, we have the square root of 1 plus, this here is just a2. The square root of 1 plus, and that's just a1. So every entry in this list of numbers, this sequence of numbers, can be expressed as the square root of 1 plus the previous entry. So let's take a walk toward infinity. Let's see what happens. All right, so a1 is the square root of 1, which by the way is 1. The second entry, the square root of 1 plus the previous, right, so that's the square root of 2. The third entry, square root of 1 plus the previous. The fourth, the fifth, the sixth, right, each one is the square root of 1 plus the previous. Well, we only took 10 steps on our way towards infinity, but it sure does look like it is getting close to something. But what? And how can we say that it is for sure getting close to something if it would actually take forever to walk toward infinity? Literally. Let's look at the other number. We could say a1 is 1, a2 is 1 plus the reciprocal of the previous, a3 is 1 plus the reciprocal of a2, a4 is 1 plus the reciprocal of a3. So every number in my sequence is 1 plus the reciprocal of the previous number. Well, let's take another walk toward infinity. So a1 is 1, a2 is 1 plus the reciprocal of 1, a3 is 1 plus the reciprocal of 2, a4 is 1 plus the reciprocal of a3, so forth and so on. It seems to bounce around a little bit, but it does seem to settle on a number. But we've only taken 10 steps on our path toward infinity. How do we know that it gets arbitrarily close to a number and stays there forever. So in fact, both of those are numbers. Both that object and this other strange object with the infinite hidden in their dot dot dots can actually be called numbers. So to say that that's true is to imply that there's some sort of convergence going on. By the way, it just so happens that both of them are equal to the golden ratio, which is the limit of Fibonacci ratios. But we're going to need some pretty heavy machinery to prove that rigorously. Even though we can see numerically, it sure does get close to that golden ratio number. So let's define what we mean by a sequence of numbers. And there's actually two equivalent ways of thinking about such a thing. One is we can say a sequence is just a function from the natural numbers to the real numbers. Right? The natural numbers are the set of integers 1, 2, 3, 4, 5, 6, 7, 8, on and on forever. Those natural numbers, that is the domain of this function, they're what we would call the index. It tells you which entry on the list you are. Another way of thinking about a sequence is a list of numbers indexed by all the natural numbers, which means necessarily that a sequence is infinitely long. For example, consider the sequence f, right? If we represent it as a function, we might say f maps the natural numbers to the interval 0 to 1, where f of n equals 1 over n. So that would be a sequence, right? 1, 1/2, 1/3, 1/4, 1/5, so on and forever. We can also describe the sequence as an index list. A subscript n from n equals 1 to infinity is, as I said, 1, 1/2, 1/3, 1/4, 1/5, so on forever and ever and ever. So what does it mean if we say that a sequence converges to a limit? Well, a sequence converges to a limit if it arrives and remains forever after arbitrarily close to that limit. Right? So arrives, remains forever after, arbitrarily close to the limit. Arbitrarily close to the limit is really the key phrase. It may never actually hit the limit, meaning it may never get there, but it'll get as close as you like. And once it gets as close as you like, it'll stay there in that vicinity forever. So stated more technically, stated using mathematical jargon, we say a sequence converges to a limit L, which is a real number, if and only if, for all positive epsilon, there exists a natural number big N such that for every single little n greater than or equal to big N, the difference, an minus L, is less than epsilon, right? The difference in absolute value, because it doesn't matter whether an is to the right or to the left of the limit as far as the distance from L is less than epsilon, where epsilon is arbitrary. Now, how does that technical definition match that first definition? Well, when we say it arrives, that corresponds to big N. Big N is the point where it gets and remains within epsilon of the limit L. When we say it remains forever after, that's because for all indices greater than or equal to that big N, I'm within epsilon of my limit. So that's what we mean when it remains forever after arbitrarily close. The arbitrariness, let's go with arbitrariness. I don't know if that's right, but that's okay, I'm a mathematician. The arbitrarily close comes from the fact that epsilon is an arbitrary positive number, any positive number, as small as you like. Right, so it's epsilon is arbitrary, and the difference between my sequence and L is less than that arbitrary positive number. So let's work out an example. Let's prove rigorously that the sequence we just discussed converges to 0. Goal: show that for any arbitrary positive epsilon, there's a natural number n, which may depend on epsilon. It almost certainly will depend on epsilon in most cases. But for any arbitrary epsilon, there exists a number, a natural number, that is a positive integer, n, that would guarantee that 1 over n minus 0 is less than epsilon for all n greater than that one big N. Now, since little n is a natural number, it's greater than or equal to 1, which is greater than 0, so 1 over n is positive. So the absolute value of 1 over n minus 0 is just 1 over n, meaning that we can drop the absolute value signs here. We don't need them. Therefore, our goal can be restated that for any arbitrary positive epsilon, there is a natural number n, which may depend on epsilon, that guarantees 1 over n is less than epsilon. For every n greater than that big N. Well, if we just read that new goal, I'm really asking, can I make 1 over n arbitrarily small? And of course I can. Since the naturals are unbounded, for any positive epsilon, there is a natural number greater than its reciprocal. In other words, for any positive epsilon, there exists a natural number n greater than the reciprocal of 1 over epsilon. Now, if little n is bigger than, or that is greater than or equal to the big N, then 1 over epsilon is less than big N, which is less than or equal to little n. By transitivity, that implies that 1 over epsilon is less than little n. I can multiply both sides by the positive number epsilon over n and deduce that 1 over n is less than epsilon. And since epsilon was an arbitrary positive number, we have met our goal. Why is that? Well, for any epsilon greater than 0, there exists a natural number n such that for all little n greater than or equal to big N, 1 over n, which is equal to what? The difference between my sequence entry and the limit 0, right? 1 over n is equal to that, is less than epsilon. So we've just shown, if I take all the highlighted in red parts and put it together, that 0 satisfies the precise definition of a limit. So we've met our goal. And so we've completed our first proof that a sequence converges to a limit. Now, like many of the topics we're going to discuss, it's nice to have different perspectives. And a neighborhood allows us a different way of thinking about sequence convergence. So a set of real numbers is called a neighborhood of x if that set contains an interval centered at x with a radius of epsilon, in other words, epsilon to the left and epsilon to the right, for some positive epsilon. That's really another way of saying U is a neighborhood if x is an interior point. In other words, there's some space between x and the edge of U, wherever the edge of U may be. So for example, the interval 0, 1, the open interval, is a neighborhood of 2/3 because 2/3 is on the inside. There's some space between 2/3 and the edges. So just to give a pictorial example, we see the interval 0 to 1, we see 2/3 firmly on the inside. So there's an epsilon radius, right? Epsilon to the left and epsilon to the right, for which 2/3 is the center, and that set, x minus epsilon to x plus epsilon, is contained inside the neighborhood. So in this example, we just illustrated that epsilon was specifically 0.1. So as long as there is a x minus epsilon to x plus epsilon open interval contained inside the set, then that set can be called a neighborhood. Of course, I could have gone really any epsilon to the left and any epsilon to the right, so long as epsilon was less than 1/3. Then x minus epsilon to x plus epsilon would have been contained inside the interval 0 to 1. Now sometimes we may want to specify a neighborhood of a particular size. So the open interval that has x at the center, that goes epsilon to the left and epsilon to the right, is called an epsilon neighborhood of x. So now that we have an understanding of what a neighborhood means, right, basically a neighborhood of x is a set that contains x on the inside, not on the boundary. So this gives us an alternate definition of a limit. Of course, it's a theorem because we're going to prove that this new definition is equivalent to the original definition we gave. And so this we'll call the neighborhood definition of convergence to a limit. The sequence an converges to a limit L if and only if every neighborhood of L, every single one, contains all but a finite number of elements of the sequence. So we'll prove it, and as this is an if and only if statement, the proof requires both directions. So we need a forward direction. And let's just think about this for a little bit. If an gets arbitrarily close to a limit, L, then if I go epsilon to the left and epsilon to the right, at some point my sequence gets within that epsilon radius and stays there forever, right? Remember, it gets arbitrarily close to L and it stays forever after arbitrarily close to L. And so that's the infinite number close to L, and outside of that radius of epsilon to either side of L, outside of it, there's only a finite number of sequence entries. Okay, so now that we understand the idea, let's give a rigorous proof. Suppose an converges to L in the original definition sense. Well then, by definition, for all positive epsilon, there's a natural number n, so that for all n greater than or equal to big N, the difference between my sequence entry and L is less than epsilon, so long as my index little n is bigger than or equal to big N, right? Now, what is big N? It's a natural number that we're guaranteed to exist, right? We don't know which sequence we're dealing with, so we don't know the specific natural number, but we're guaranteed of its existence. It has to exist because if it didn't, then an wouldn't converge to L. The fact that an converges to L means that there is some natural number n. There's some number, it exists, and for every little n bigger than or greater than or equal to it, this is true. Now, when we say an minus L is less than epsilon, we mean that an minus L is at most epsilon away from 0, whether to the left or to the right. One way of saying that is an minus L without the absolute value is sandwiched between negative epsilon and epsilon. If I add L to all three sides, I get an is greater than L minus epsilon, but less than L plus epsilon, which is equivalent to saying AN is in the open interval L minus epsilon to L plus epsilon. And that's true for all little n greater than a specific natural number. And of course, there are infinitely many little n greater than or equal to big N. So what about my sequence entries before big N? Well, maybe they're in the interval, maybe they're not, but there's only a finite number of them. Also, notice that epsilon was arbitrary. So we've shown that every neighborhood of L, which contains some interval, L minus epsilon to L plus epsilon, contains infinitely many sequence entries, right? Specifically, all little n bigger than or equal to big N, right? Specifically, what is there in red. Thus, for every single neighborhood of L, there is an n for which all sequence entries except a subset of the entries A1 through A big N minus 1, right? Some of those, right, maybe 1, maybe 2, maybe all of them, maybe none of them are contained in it. But so long as I have a set of size less than or equal to n minus 1, even if that set is size 0, that's a finite set. And those are the only entries in my sequence that are not possibly inside the neighborhood. So we've shown the forward direction. Now let's show the reverse direction. Suppose every neighborhood of L contains all but a finite number of elements of the sequence, right? Now our goal is to show that L satisfies the original definition of sequence convergence. That if this new definition is true, then the old definition must be true. So if every neighborhood of L contains all but a finite number of elements, then certainly every epsilon neighborhood contains all of my sequence except for a finite subset. Let's consider the finite subset not contained in my epsilon neighborhood. Since it's finite, it has a largest index. We're going to call that largest index big N. Because any finite set of numbers, in this case a finite set of indices, has a maximal element. Well, for every little n greater than or equal to that big N that we're guaranteed to exist, in other words, for everything not excluded from the epsilon neighborhood, I must be in the epsilon neighborhood. In other words, for every little n greater than big N, a little n is included in my epsilon neighborhood. By definition, that means AN is greater than L minus epsilon, less than L plus epsilon. If I subtract L from all three sides, I get negative epsilon is less than AN minus L, which is less than epsilon. Therefore, AN minus L is less than epsilon. Right? That follows from our absolute value theorems. That was one of the results of the absolute value theorem. QED, we've shown the result. Wait, why? Why have we shown the result? Well, because we've proven that L satisfies the original definition of a limit. You don't believe me? Well, look, it's actually right there in red. For any epsilon greater than 0, there exists a natural number n, and for every little n greater than or equal to big N, the absolute value of AN minus L is less than epsilon. That's precisely the definition of the limit originally, and we've proven exactly that. So now we have two ways of showing something is a limit. We have two tools to use anytime we want to show that a sequence converges. Or if we know that a sequence converges, we have two ways of describing what happens. Which tool do we use for which situation? Well, it depends on which gives us the most readily usable result, or which is the most simplest to implement. In the next lecture, we'll have liberty to choose which definition we want, and we'll do it both ways, just so that we can have a beauty contest of which way is best. But to see that proof, you'll have to tune in next time. That's it for today.